Conservation of energy. Work has a non-zero value only for force components in the same direction as an object's motion. The gravitational force always points down, so lateral motion requires zero work by the gravitational force. The only impact on gravitational potential energy is the vertical component of the motion. So consider the case of the diagonal motion here. Delta UG, or GPE, is calculated for both the x and y components of the motion. Right, this is the x component, this is the y. Only the y motion gives a non-zero value. Here's the x component, the potential energy. Change in potential energy is minus the work done by the gravitational field. We put in F delta x cosine theta. We have 90 degrees. The gravitational force is down, and we have lateral motion here. That angle between them is 90 degrees. There is no change in potential energy as you move laterally. However, if you move in the y direction, you get mg delta y. The same answer for the potential energy is found for the vertical path or any other path. If we just went up here, we would get this answer. If we do any other path, all it considers is the vertical piece. This is the first property of a conservative force. It doesn't matter what path the object takes, the same amount of work is performed and the potential energy is the same. Conservative forces have a second property. If an object is moved in a closed path, that is, it begins and ends at the same point, like this here, the net work done by the force on the object is zero. So in this case, the object starts and finishes at height 0 equals 0. So we use our work equation here, and we find out that no work is done and the potential energy doesn't change. As the object was going up, the gravitational force does negative work, decreasing the object's kinetic energy and speed. On the way down, positive work is done by the gravitational force, increasing its kinetic energy and speed. The sum of the work done over the closed path is zero. Here's our two properties of the conservative force. The work done by conservative force on an object depends only on its initial and final position. Another way of saying that, it is path independent. 2. The work done by a conservative force on an object is zero on a closed path. That's when your initial and final position are the same. And again, you don't care how you got there. So what would a non-conservative force be? Well, it does not follow the two properties of a conservative force. The path taken does impact the work done, and the work done on a closed path is not equal to zero. Friction is the most common example of a non-conservative force. Friction force opposes motion. The longer the path taken by an object, the greater the work done by the friction. An easy demonstration of the non-conservative nature of the friction force is to move your hand over a smooth surface, like your desk. Movement in a straight line may warm your hand a little, but if you move your hand back and forth and take a longer path to get to the final position, it heats up more. Your hand experiences more frictional force. More work is done over the path of motion. A unique potential energy for this force cannot be calculated, as the energy difference between 2 points will not always be the same. It depends on the path taken. The gravitational force is a conservative force. The path that an object takes has no bearing on its potential energy. The change in potential energy depends only on the initial and final heights. Each of these three paths results in the same change in potential energy for an object moving from h0 to h. The gravitational force is a conservative force. The friction force is a non-conservative force. Consider a falling object and neglect air friction. For the closed Earth object system, the gravitational potential energy at the start of its fall is equal to the kinetic energy when it hits the ground. The total energy does not change. When friction occurs, the Earth object system is open, and the air friction force performs work on the object to slow it down. Its kinetic energy when it hits the ground is less than its initial GPE. The air friction force is the reason the Earth object system's energy decreases and is considered an open system. This time, for a falling object with no friction, specify the system as just the falling object, not including the Earth. Then it is an open system and energy is not conserved. For this case, gravity is an external force performing positive work on the object, causing it to fall. The object at rest had zero energy, but as it fell, it gained kinetic energy due to the work done by the gravitational force. So you have to be careful when you choose the system for your problem to ensure you get the right answer and to see whether you can use conservation of energy, which we'll be discussing shortly. When an object is dropped in the Earth object system, its energy is constant but changes forms. The gravitational force is an internal force in the system and doesn't change the total energy in the system. It only had gravitational potential energy at the beginning because it had height but no velocity. Just before striking the ground, or the person's hand, it only had kinetic energy as it had velocity but no height. In between, it had some of both. 3 types of energy have been discussed so far: kinetic energy, gravitational potential energy, and elastic potential energy. The amount of energy present can be changed by the application of a force over a displacement, work. The friction force dissipates or removes energy from a system. Open and closed systems have been described, and it is now time to describe several other types of energy leading to the complete conservation of energy equation. Other types of energy include, and this is not inclusive, different types of potential energy that involve a conservative force, such as the electric and magnetic forces. Sound and water waves carry energy. Energy stored in capacitors. Electromagnetic radiation. Heat transfer from hotter objects to colder ones. Internal energy. Now that's based on the temperature of objects, also called thermal energy. And nuclear energy. Total energy, E, is conserved. It cannot be created or destroyed. Consider an open system where energy and matter can be transferred from the environment into and out of the system. We're going to select a special open system that has the following energies: kinetic energy, mechanical potential energies, that's gravitational and elastic, which we've already covered, and the internal energy, that depends on the system's temperature. So we have our little equation here. The energy is Ke plus potential energy gravity, potential energy elastic, and internal energy. The total energy of an open system can be changed by the transfer of energy from, first of all, work done on the system by non-conservative forces like friction, and the other types of energy that we talked about a few slides ago. And to save ink, we're going to just replace them with delta E other. So that would be the change in energy from sound and water waves, energy stored in electric and magnetic fields, electromagnetic radiation, heat transfer from hotter objects to colder objects, and nuclear energy. The change in the energy of an open system, then, is this formula here. So there's a lot of things on this line, but we took the previous equation for energy and just added a change here. So kinetic energy can change, gravitational potential, elastic potential energy can change, and the internal energy can change. That's going to equal work plus the sum of all these changes. For this course, the change in energy equation is simplified by only allowing work to change the energy of the open system. The other energies are removed from the equation. They will not be covered in this course. AP Physics 2 will pick them up. So now we have our change in energy is going to equal work. This extends the work kinetic energy equation that was derived earlier in the unit by adding the potential energies and the internal energy. Now let's move to a closed system. For a closed system, there is no energy or matter transfer between the system and the environment. Work cannot be done on a closed system and change its energy. So the right side of the total energy equation is equal to 0. The open system total energy equation reduces to the conservation of energy equation for our closed system. So here's the open system that we've been dealing with, where the change in energy is equal to the work done on it. But now the work done is 0. So for a closed system, we have delta E equals 0, and that is the conservation of energy. One more step. The conservation of energy equation is further reduced to the conservation of total mechanical energy, which only includes change in kinetic energy and the change in gravitational potential energy and elastic potential energy. It does not take into account the internal energy. This is all equal to 0. This is the equation that will be used for most of our calculations for closed systems. Motion problems can certainly be solved through the application of Newton's laws to free body diagrams. However, for non-constant forces or objects moving in 2 dimensions, the calculations can be complex. By using the conservation of total mechanical energy wherever possible, it doesn't matter what the forces are doing or how the objects are moving. You just need to consider the original and final states. This, along with the fact that energy is a scalar, makes the solutions much easier. When energy is transferred into a system, delta E is positive. When it leaves the system, delta E is negative.